Is it possible to bit bang a floppy drive? Let's find out. For this project, we need a microcontroller. I'll go with the Teensy 4.0, but what can we do with it? All the lower pins here are ground. Why do they need 17 ground pins? I'm not sure, but the fun stuff happens in the upper pins. Each one has a special function. Some are things that we can control, activate the motor, change tracks, write data. Other pins are outputs, like read data, index, track 00. These will give us valuable signals. Okay, let's wire it up. That schematic, by the way, was really hard to find. Floppies became obsolete around the year 2000, and there are only remnants of documents scattered throughout the deep web. Okay, it's all hooked up. Let's do this. So the first thing is to get the motor running. It's actually quite simple. We just have to manipulate two different GPIO pins. The first GPIO pin is the motor pin. You pull that low, the motor will start spinning. If you want to do anything else in the floppy drive, you also have to pull the drive select pin low, and that will activate the rest of the functionality that the other pins offer. Nothing. Oh, there it goes. Motor is spinning. Now what will it take to actually read from a disk? Floppy disks don't store ones and zeros like you might imagine. Instead, they rely on flux transitions, which are written to the magnetic strip inside the floppy disk itself. The timing between each transition indicates some encoded binary value. There are three kinds of pulses you can sample: short, medium, long. These will translate to binary. The floppy disk uses MFM encoding, which is a protocol that mixes the clock signal with the data signal in a compressed, deterministic way. So every even bit of data is real, every odd bit is possibly a clock signal, maybe not. Okay, let's implement this. Some assembly required. In order to sample the pulses, we actually have to kind of get pretty low level here. The reason is that we are counting cycles. Yes, that is the level of performance we have to get to so that we can get the timing exactly right. We're talking microseconds. And if you use a built-in delay method or something like that, it often comes with some overhead, and that'll just totally ruin your code. From assembly, we're able to time the low to high transition. So if you think of it low to high, that'll be basically one block of a pulse. The timing is key because based on which pulse we get back, that will determine the binary value that the underlying data is representing. From there, it's a pretty simple matter of piecing together the signal and then extracting the data from it so you can have a clear picture of what you're reading off of the magnetic flux. We can verify this pulse method is working by running it for the whole entire cycle of a floppy disk and then bucketing the results and counting how many of each pulse we got back. If the distribution seems normal-ish, it's probably good. If you have too many of a particular bucket, that's a clear indication that your timing is not quite right. And it probably has to do with how you're counting cycles and the assumed speed of the CPU. Okay, now that we can read pulses, it's time to decode the signal and then read some data off of a floppy disk. Now, writing to a floppy is actually much easier than reading from it. All you're doing is transitioning a few GPIO pins from high to low and then waiting in between them, and you're able to recreate the same pulses that we had just read from the floppy disk. So we're doing that same operation, but in reverse. The hardest part is actually encoding the data because you have to use something called modified frequency modulation, or MFM encoding. You can check out all this code on GitHub if you'd like to see it in detail. I also threw together floppy.cafe, which is a rad website outlining all my learnings from this project, and it includes an interactive MFM encoding tool should you want to learn more. Thanks for watching. I hope you enjoyed this video. Let me know what you think in the comments, and remember to subscribe for more content.